Hello, North Tahoe High physics students. Once again, we are here for what we hope to be a quick video lecture on the basics of wave characteristics. What do we need to know about waves, all waves, to move forward and study these things in more detail? So our objective today is going to be to figure out, first of all, what does a wave do? If a wave has a job description, what do all waves do? We talk about sound waves, light waves, seismic waves, water waves. They're all waves because they all behave similarly. We also want to know what are the two types of wave motions. So we classify waves mostly into two different types, and what measurements or quantities characterize a wave. So let's go ahead and get started with the first one. What does a wave do? Well, all waves have this in common. Their job description is to transport energy and not mass. So if we haven't thought about that before, we have to sort of delve into what does that mean specifically. A wave can travel through a material, and in this case we're talking about a wave traveling through the ocean or through water. But the water itself doesn't move appreciably. When we have an ocean swell travel across the Pacific, the water on the coast of Japan does not end up as the water on the coast of California. Currents transport mass, but waves themselves actually transport energy. And we get a sense for that if we've ever watched surfers lined up waiting to catch a wave. The wave itself here moves, the energy propagates one way, but the surfers don't necessarily move with it. They just go up and down as the wave travels underneath them. So the water and the surfer, the mass, isn't actually moving in this situation, but the energy is. So all waves will have this characteristic. They transport energy, not mass, appreciably. A little bit of motion, as we'll see, but the mass doesn't move from point A to point B. Now, what would it mean if waves did transport mass? Well, we think about my voice reaching you in class. My voice travels, of course, as a sound wave. So the sound actually leaves my vocal cords, which would be somewhere here, and it reaches your eardrum, which would be somewhere here. And that can happen, right, without the physical mass coming from my throat and then hitting you as though I'm breathing you on the ear. Right? I mean, no one wants that. That's creepy. That's kind of gross. So the mass from my mouth, or the mass from anyone who's speaking's mouth, doesn't actually have to touch you in the face, but the energy from the vibrating vocal cords in this case does travel through the air without the air moving, and that's what reaches your ear. Same thing is true of sitting on the sun or feeling the sun's warmth on a sunny day. You can receive or feel the sun's energy as light waves traveling from the sun without physically having to have the sun actually touch you, the masses of the sun. That wouldn't be pleasant. No one would like that. So waves transport energy, not mass. Two main kind of waves then that we're going to have what are called transverse waves, so that's an important vocabulary word, and a longitudinal wave. And we'll see characteristics or examples of both. But what does the word transverse actually mean? In this case, the person's hand is making a wave in what looks like a slinky. So the slinky itself, remember, the individual coils, say this coil, doesn't move very much. It does move up and down, but it doesn't go from point A to point B. The wave itself does. The energy propagates through the slinky. Transverse means that the disturbance is perpendicular to the direction that the wave travels. So the disturbance is up and down by the hand. The wave itself travels horizontally. So that's a characteristic of a transverse wave. The disturbance is perpendicular to the wave direction of propagation. Water waves are transverse. Light waves, we'll see, we model as transverse waves. Most of the waves, we think of a classic wave, we're thinking of transverse waves. The other wave is called a longitudinal wave, and that happens when the disturbance, in this case the person is pulling backwards and pushing on the slinky, the disturbance is parallel or anti-parallel to the direction of wave propagation. So when we watch this wave, this would be an example of a sound wave, we don't actually see the slinky move up or down, but we see these regions of compression sort of pulse through the slinky itself, and likewise these regions of expansion called rarefaction also pulse through there. So the wave itself is traveling in this direction, and the disturbance, the expansion and the compression, is also traveling in that direction. So that's a longitudinal wave. And sound waves, or in some forms of seismic earthquake waves, are longitudinal waves, and we'll talk about those also in detail in this class. So important parts of wave measurements, if we're going to talk about waves, we've got to have some common vocabulary. Well, how is one wave different or similar to another? So let's talk a little bit about this. Here's a picture, a drawing of a typical wave, kind of a sine wave looking thing. And there's a few important things that we need to know. This A, the distance from a rest position to the top of the wave would be called a crest. The bottom of a wave would be called a trough. That distance, they put the letter A in this graphic, that's the amplitude of a wave. For a sound wave, the amplitude determines the actual volume of there. That's why you might buy an amplifier or an amp for your car stereo to make it louder, because you want to boost the amplitude of the sound wave. Another really important idea, super important for moving forward, and luckily it's really easy, is the idea of a wavelength. So the wavelength itself is just defined as the distance from two similar points on the wave. So in this case, the wavelength is crest to crest, but I could also make the wavelength or make the measurement from trough to trough, or I could also measure it from here, where the wave crosses the resting position. So right here, 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 and here. That is called a node. So there's no motion up or down in this case, or no disturbance in that node. That's called a node. So a wavelength could also be measured not from node to node, but across every other node. And the wavelength itself is usually given the Greek variable lambda. So it looks like that, and we'll see that in script all the time. But the wavelength is going to be super important to moving forward. So a few important wave quantities. If we're going to talk about it, we need to be able to make measurements and compare waves, and in physics, of course, we're going to use numbers. So one of the really important aspects of waves is describing a wave by its frequency. The frequency is determined by the number of waves that pass a point every second, and we'll practice this on the next slide. It's measured then usually, sometimes we'll call it waves per second. And sometimes we'll call it cycles, a one wave cycle per second. But we also have a unit that is cycles per second, and we call that a hertz, H-E-R-T-Z, and that's abbreviated HZ. That's what you tune to on your radio station. If you listen to 101.5 on the radio station, you're tuning to the frequency, and that's 101.5 megahertz. So 101.5 million hertz, million radio waves are hitting the antenna every second. Another important aspect is the period. The period, a little bit easier to grasp maybe. It's simply a time. It's the time in seconds for one complete wave to pass. So the unit for period is just simply seconds. How many seconds does it take a complete wave to go by me? And these two are related, and they're inversely related. If I know the period, which is given the variable t, maybe we can think of because it's measured in time, it's inversely related to the frequency. And if I know the frequency, it's inversely related to the period. So those two are interchangeable. If we know one, we by definition know the other. The last thing we want to talk about is the wave speed, and that's a simple definition. It's just simply the speed of the wave. Sound travels at the speed of sound. Light travels at the speed of light. You may be aware that tsunamis in the ocean travel at hundreds and hundreds of miles an hour. And waves in Lake Tahoe may travel at a few miles an hour. We're going to be able to calculate those pretty easily using some PreBasic measurements. So let's look at this picture at a set or a train of waves coming into the beach here, and kind of put our measurements and our definitions with there. Imagine that we have a surfer kind of out here in the middle of there, and this surfer is physics inclined, as many surfers are, so they're on their board, and they're just standing there. So maybe it's a paddle boarder, right? Not traveling with the waves, just noticing the waves coming by. So one of the things then that we talked about was the wavelength. And in this case, the picture, you can see the wavelength really well. It's the distance from crest to crest. So that would be the wavelength in that case. The surfer may also be interested in, knowing how many waves pass them every second. So let's just say, not every second, let's just say that this surfer counts for a minute for 60 seconds. And they notice then that in 60 seconds, 20 waves came by. So this surfer could do the math and they'd notice, well, that ratio is 1/3. So what they've calculated is the frequency of those waves. They would say the frequency of these waves is 1/3 or 0.33 hertz. The last thing that the surfer could do with our measurements then is calculate the period. How long does it take one wave to come by? So what we just learned last time is the period t is inversely related to the frequency. So if the frequency is 0.33 hertz, then the period must be 3 seconds. So put that in and see if that makes sense. If there are 20 waves and each wave takes 3 seconds to pass, a total of 60 seconds of time would have elapsed. So again, what we've learned here then is period and frequency, and that last one, which we're going to really practice in class, is what about wave speed? How do we calculate the speed or the velocity v of a wave? Well, it's simply going to be a distance divided by time, like all speeds, but in this case the distance is a wavelength, lambda, divided by a time or a period. So that's distance divided by time. That's meters per second. We could also see it this way then, lambda times frequency, because remember, this relationship holds true. So we're going to practice all of these. Certainly by no means are you going to be experts after this quick video, but you will have enough to begin moving forward. So take the Google form, check for understanding, and tomorrow when we show up to class, we're going to work with these ideas.